Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be looking at three-phase electricity. Now this follows on from our series on electrical engineering, so if you haven't watched the previous videos on this so far, then please do this first. Links are in the video description below. Coming up, we're going to be looking at how a simple AC generator works, then we'll look at a single-phase power, then two-phase power, and then finally three-phase power, as well as how three-phase power is used and why, also why we don't use 4, 5, 6-phase, etc. power. So first of all, let's start with a simple AC generator. We'll start with a single phase to understand what's happening, and then we'll add in other phases until we get to three phases. Let's take a copper wire and wrap it into two coils, then place these coils opposite each other within a stator and connect the ends together to create a complete circuit. Now, if we place a magnet in between these coils and we start to rotate the magnet, then the magnetic field will disturb the free electrons within the copper wire and an electrical current will begin to flow. We've covered how the free electrons flow in our previous video on electricity basics, so please check that out if you've not done so already. Links are in the video description below. As the magnet rotates, so does the polarity of the magnetic field. As you can see in the illustration, the north and south pole of the magnet are rotating, and as they rotate, they pass across the coils, which force the electrons to move. Notice the lines of the magnetic field are in these oval shapes on each side, and they meet through the central axis of the magnet. You can think of these as one side being positive and the other side being negative, and in between these ovals, the magnetic field is neutral. You can see that the intensity of the magnetic field increases on either side until the center, where it is at its maximum strength, and then it decreases again until it gets back to the neutral point. So as this field rotates through the coil will experience an increasing intensity of the magnetic field's positive half, and during this increase, the free electrons within the copper coil will be pushed and begin to move faster and faster in one direction up until it reaches the maximum point of the magnetic field. Then, as the magnetic field decreases, the flow of electrons will begin to slow all the way until it reaches the neutral point where no electrons will flow. Then comes the negative side of the magnetic field, and as this passes through, it's going to pull the free electrons backwards. Again, the flow of electrons will flow faster and faster up until the maximum point of the magnetic field, and then it will decrease back to the neutral point. This is why AC electricity is called alternating current, because the current of electrons alternates in direction backwards and forwards, just like the tide of the sea. If we were to plot on a graph the speed of the electrons flowing during the rotation, then we would get a sine wave pattern. In this sine wave, you can see that the electrons are stationary at the start in the neutral zone, and then the speed increases through the positive half all the way up to the maximum, and then it begins to decrease all the way back down to the neutral, where no electrons will flow again. After this comes the negative half, where the electrons speed up to the maximum point, and then they begin to slow down again until the magnet has completed one full rotation, where this will then repeat. This complete rotation is known as a cycle, and the number of cycles per second is called the frequency, which is measured in hertz. You've probably seen 50 Hz or 60 Hz written on your electrical goods. This means that the generator of the power station is completing a full rotation either 50 or 60 times per second. So the direction of the current is therefore also changing 50 or 60 times per second also. When it is written on electrical products, this is just telling the user what type of electricity the product should be connected to. Now, coming back to the sine wave that we saw earlier, this plot of current also represents power, and if we connect a lamp into the circuit, we'll see that it will increase in brightness all the way to the peak, that maximum point, then it decreases in brightness all the way down until the neutral point where the lamp is actually off because no current is flowing. But then it will increase in brightness again as the negative half of the cycle comes through and the electrons start to flow back through in the opposite direction until again it reaches the neutral point. So, at these points in the cycle, the lamp is not producing any light, and at these points in the cycle, the lamp is not very bright, so it's not of much use. So if you're working in a room and this lighting is flickering like this, it's going to get really annoying. To improve this, we can add another set of coils or a second phase into the generator. And we can do this by placing the coils 120 degrees rotation from the first set of coils and then connect this up to another lamp. This rotation means that the coils will experience the changing intensity of the magnetic field at different points in time. The first coil reaches its maximum current and brightness, and as it decreases, the second coil will begin to increase. This has improved the lighting, but there's still a gap which will cause a flicker. So we can add in a third set of coils or a third phase, and this will mean that one of the lamps are almost always at its maximum brightness, so the lighting is nearly constant. There are still some small gaps between the phases, and you could keep adding more and more phases to fill these gaps, but this will become more and more expensive to keep running all these cables. So 3-phase became widely accepted as it's a good compromise between power provided and cost to build. Now in the real world, you're not going to use 3 different lamps on different phases to create lighting. The lamps in your homes are all on single phase, but they are flickering. It's just that they are turning on and off so fast that the human eye can't see it unless you record the lamp in slow motion. A more practical application is to power electrical induction motors and other commercial and industrial equipment, as 3-phase will provide a lot more power to these items, meaning you can pump water higher or you can run motors faster, etc, etc. Power is generally generated and distributed in 3-phase, and transformers are used to change the voltage. If you want to learn how transformers work, we've also covered that too. Links are in the video description below. Now, one of the interesting things with 3-phase power is that you can connect all 3 phases and power large industrial equipment, or you can also connect to only one of the phases and also power small electrical goods. This is generally how large tower blocks and skyscrapers distribute electricity through the building. The lift motors and air conditioning pumps, etc. will need 3-phase power, but the computers and office equipment will need single-phase power. So they distribute 3-phase power up the building and then draw off from this as needed. The same occurs with the distribution of electricity across a city. Houses will be connected to only a single phase because they do not require much power, whereas a large building will be connected to a 3-phase supply as they will require a lot of power. Okay guys, that's it for this video. Thank you very much for watching. I hope this has helped you and you've enjoyed it. If so, then please don't forget to like, subscribe and share this video, and also follow us on Facebook, Twitter, Google+, Instagram, as well as our website, theengineeringmindset.com.